Okay, so if you've seen too much of me, blame Sheikh. He's the one who asked me to write the second paper. Uh, so this is a related but different topic. It's about a particular way of training. And if you're going to do training, you have to answer questions about who, what, why, how, and so what. So I'll address these questions in this order. So who? Typically, we think of students of introductory programming courses in this workshop. But I'm also thinking of advanced students who don't know threads, a lot of them who don't. And I'm also thinking of faculty who need to be trained in concurrency. And what? Fork join concurrency. Okay, so this is something that everybody does, and I'm going to talk about fork join concurrency here also, where we have work divided among workers and collected later by joining. So we have a fork step, we have a partitioning step where we partition the work, we have a synchronization step where we make sure that we don't step on each other's toes, and we have a join step. So why? So the classic approach to teach such concurrency is use a declarative mechanism, and that's great. But one disadvantage of that is that it hides many of the fundamental concepts underneath, like there's a per thread stack. Somehow these loops got replicated. What happened underneath? There's a reduction variable that got replicated. There's synchronization going on underneath. So who should know this? Maybe not the introductory students, but at least if you're teaching, you should know what's going on underneath, because there may be some curious students who want to know. And given enough time, so should students. Time is the big deal. How do you find time? If you're talking of a teacher training workshop, sometimes it's a single day. Like the first time I saw a workshop that Sheikh was giving, that was exactly one day. And how to find time there, especially if you're doing OpenMP also, there, how to find time for Java threads or procedural mechanisms. And if you're adding things in a course, if you're adding things to a sequential course, they're already crowded. And to find time for even declarative mechanisms is hard, and procedural is going to be even harder. Okay? And these are less of a problem if you restrict your time to just 1 hour. Okay? Why 1 hour? Well, there was this workshop at Tennessee where they had the lunch was working lunch. And lunches go to 90 minutes often, so maybe you can teach this stuff during a working lunch. Okay? When somebody's away, a professor is sick, that happens, or away at a conference, that happens a lot in the States. You can ask the TA or some other instructor to go and take their class, but they won't quite do what you wanted to do. So why not go and teach concurrency during that time period? Okay. At the start of a course, if you have a lab session, there is no theory to practice, so maybe you can sneak it there. This is all about sneaking in somehow concurrency. And at the end of a course, when people are really tired and there's not enough time to go and write assignments for what's done in the last week of classes, maybe you could slip this in. Okay? I live in the South in the States, and the sky sneezes a little bit and the university closes. Okay, this is very different from when I was in the Midwest. So there are snow days and other unanticipated closures when you can do this. And many courses are designed to spare 1 hour. Okay? So this is a big deal, that somehow can we do it approximately within 1 hour, maybe 1.5 hours, maybe even 2. And if you're teaching concurrency, you've got to have hands-on programming. And I've been talking about the instructor not being available, so we'd like to do this lectureless. Okay? The TA could be available, but not the professor. Okay? So we want somehow lectureless, theory-oriented practice. And what does that mean? Well, you're given, Sanjay mentioned in his plenary talk that it's good to go and have students given code that you've written already. Okay? So you give them some code that you've written, that's a model, and it has a lot of explanations. Okay? Through comments. So it has conceptual comments, it has output that explains what's happening, it's got instructions to experiment with the code, it's got challenges that going up high in the Bloom's taxonomy, that they should try to overcome, and it's got testing code to figure out whether your challenges are being met or not. And the testing code also is helpful in trying to explain what's happening. Okay? And if all else fails, at least for now, before AI takes over, we have a TA to go and help the student also. Okay? TAs perhaps. And to make sure the students learned what you intended to, you add a quiz also, okay, which they can take on their own. So no professional. And so these are pretty abstract concepts. Let me just give you examples. So what are conceptual comments? When you think of concepts, typically they describe the algorithm that the program follows. Here you also describe the mechanisms used in the algorithms, because you assume they don't know these mechanisms. So for instance, you explain the concept of a thread within comments before you go and start a thread. Okay? And the thread is a stack of independent stack, for instance. Normal output, you give the input, you show, maybe display the input and give the output, that's it. And the output here illustrates the mechanisms and algorithms used through tracing of intermediate steps. Okay? So here, the blocking semantics of join can be explained and illustrated through the output, for instance. Okay? So we talked of asynchronous versus synchronous distributed computing, and that kind of stuff occurs here too. Okay? Test results. So typically test results just test your final output. Here the test results also go and look at the traces to see whether you're on the right track. So for instance, it can say that, look, there's no concurrency here. And experimental instructions, basically experiment to understand the semantics of mechanisms. So for instance, you can go and comment in and comment out synchronized keyword to see what happens. Okay. Challenges, so it involves changing the given algorithm. So for instance, you can fix a problem with the specified method for forking and joining, which is what's happening here. So that's the abstract idea. There's nothing to do with concurrency so far, but we have used it for concurrency. And so this is not all theory. And what I'll do next is show how this model has been used for concurrency. I define concurrency as teaching forking, joining, partitioning, and synchronization. So let's go and talk about how we can teach forking and joining this way. So here's a piece of code that some of you have dealt with actually, that goes and forks and joins. It seems very correct. It's got a fork, it's got a join, it's going through all the threads and creating these threads, but it's wrong. And here's an explanation comment that explains what fork does. Okay? Stuff that you would go to Java docs for, it's in the comment, so you don't have to go far. So it tells you what join does. And here's some output that's telling you what's happening. Okay? It's saying, look, thread 13 got started. the starting thread is waiting for it to finish. Thread 13 is running right now. Thread 13 finishes. Starting thread is resuming execution. And this is starting now thread 14. And you get the whole idea. Okay? And if you didn't quite get the idea and what's wrong, here's some test result that tells you that, look, between the first and the last output of a thread, there is no other intermediate output. Okay? And if you still didn't get the idea, and in the experiment, some students didn't, then the TA went and explained what the problem was. He said, look, what is it doing? Well, it's doing forking, then joining, then forking, then joining. And then said, what should it really do? They said fork all, join all. So they get the idea there. Okay? And then they fix it, and I won't. Some of you are still doing the exercise, so I'm going to not focus on the fix too much. Okay? And just to make sure that the people who were helped really understood what's going on, there was a quiz question that says, tell me what the difference was between the traced output with the fix and without the fix. Okay? And then the answer was graded. Okay, so that's fork and join. So this is the bug there was. So typically when you partition work, it doesn't evenly divide. Okay? So there's a minimum amount of work that every thread has to do, and then there's a remainder left. So this code first calculates how much work each thread should do at the minimum. Then it says then it figures out what the remainder is, and then it figures out which thread we're talking about. If the thread is 0, it gives it all the remaining work, and if it's not 0, it gives it none of them. No, doesn't give any work. Okay? And the output shows you what's wrong. One thread gets 4 items, another thread gets 1, and that seems imbalanced. Okay? And if you didn't quite figure out how it's imbalanced, here's some test result that says, look, the difference between the minimum amount of work and the maximum amount of work should be less than or equal to 1. Okay? And so that tells you what the problem is, and there's a fix that I won't go into, which as it turns out is the hardest. This is the hardest problem. Okay? And when the fix occurs, the load is more even. Okay. And again, in this particular part, there was a lot of help requested, both in the training workshop that we talked about and in my class. So to make sure that people understand what happened, there was a question that says, how is the traced output of the buggy version different from the corrected one? And that answer was created. Okay, synchronization. So I remember attending Sheikh's first training workshop in 2018, and I think only and he was trying to demonstrate race conditions, and I think we had to go through like 1 million iterations before the race condition. In some examples were shown. It's very hard to show race conditions unless you sort of engineer things like I did here. Okay, so the idea here is that the program has to go and increment number of results. And rather than doing it directly in a high-level language, we go and simulate register, load and save. And between this load and save, I add a sleep. Okay? And multiple threads execute this code. So, and there's no lock put on this code. And so you get something like this, that one thread goes and loads 0, the other, before it can save 1, another thread loads the same value, so they both end up loading 1. Okay? And that's what happens in the trace, and the result is not what you expect. Okay? And this problem is a very non-HPC problem. Even though we are using HPC solution, it is finding all odd numbers in a set of numbers. Why did I pick odd numbers other than say prime numbers? Because the chance of this was finding all odd numbers in a random set of numbers. The chance of 2 random numbers being odd is 50%. And so the chance of collision between 2 threads is 50%. You add 4 threads, you increase the percentage quite high. So you are always guaranteed a collision, and pretty much, I mean, you can't always be guaranteed theoretically. So, and the recommended synchronization fix was just to add the lock. Okay, and that's no big deal. You're told to uncomment the synchronize keyword. Okay, and then things worked out right nicely. So at least they saw in the user interface what. And then there were some tough questions on what was happening. So firstly, we asked them, okay, how does this output differ in the synchronized and the unsynchronized case? And that people got. Okay. Then I asked them to sort of integrate 2 ideas. I said, okay, let's go back to the buggy fork join, where you forked, joined, so only one thread was executing at any one time, and you didn't put a lock. Tell me why you shouldn't have to go and put a lock there. Okay, now that seems obvious to you guys, but these guys, a lot of them haven't seen threads, and so and people got the answer that, look, if you've got only one thread active at any one time, who needs synchronization? Then came the tricky question. And this code, this load save code, was in a static method, which is called by another static method, and that was the only caller. And I asked them why, why is it equivalent to put the lock either in this method or this method? Okay. As it turns out, if you lock one static method, you lock all static methods, so it doesn't matter. Okay. And then I made the problem more complicated. The static method here, this one, is called by an instance method, the run method in Java, and that's the only method caller. And I said, is locking the run method and this method the same? Okay, and one is instance, one is static, and as it turns out, with instance methods, you get a different lock for each instance, and so I asked them whether I asked them a question to figure out whether they got that or not. Okay, so that's the exercise, and what happened? There was a PI meeting in which Sheikh, I, Sanjay, a lot of people were in that meeting, and I figured I'll kill 2 birds with one stone. I'll attend the meeting also, and I've been thinking of this exercise. So while I was away, in fact, while I was chairing a session in the working group, this exercise was given to the students, and I was more interested in what's happening there than what was happening in the workshop actually. So this was a 75-minute class, and I had 2 students, two TAs go and actually practice the problems, and they found it quite challenging, as it turns out. And this class, I allow people to, I use Zoom, so I allow people to remotely attend, and 50%, this is during lunch hour, 12:30, so people like to stay at home and have lunch. So about 50% of people come to class. I don't know what happened that day, I wasn't there. though we did record everything through Zoom. There was also one TA for the Zoom students, and nobody used them, so it was very interesting to hear David Bundy's talk about virtual workshops. That may be a problem there. And this was a programming language class, which I teach, which doesn't include concurrency normally, but I thought I'd slip in concurrency this way. And it's typically taken by seniors. If this was the first time I was doing the experiment, so I didn't want to try with introductory students. And they're in between introductory students and lecturers, so I thought that was a good example. And there are 42 students in the class. Some students were just not doing anything at all. 40 students submitted code, 36 submitted quiz answers. And it was low stake. The quiz counted for 0.5% of the grade. I have class participation grade, and for every class question they answered, they get some points. So every quiz question was like a class participation question, so it was very low stake. And the assignment was 1% of the total grade, less than that, because low stake. So here's the background they had. I actually worked on getting one of our introductory courses to have concurrency, but since I'm not the one teaching, it's not hands-on there. So some people had no background and while they were seniors. And this was happened recently, so some of older students. Some students had 90% of students had general knowledge of concurrency. I asked them how many of them actually knew about partitioning, forking, joining, and 49% said they knew that idea theoretically. And 22% students had probably taken an operating system course, so they had seen non-Java implementation of threads. Okay? The fork join fix, everybody got it eventually, with or without help. Load balancing fix, as it turns out, there were 2 tests, and if you did hardwired the solution, one test would work and not the others, so one student hardwired, and synchronization, of course, everybody got right. And remember, 96%, one student did not do the coding problem, but 1 or 2. How much help was needed? Fork join, 6% of the students who came to class. Okay, 6% of students, 50% came to class, so it's almost like 12% of the students who came to class needed help. Load balancing, 20% of the whole class needed helping. Okay, and synchronization, there was no help needed. Okay. And quiz questions, they got it mostly right. And the tricky one was, and not everybody did the class quiz, and the tricky one was the static versus instance lock thing, and 46% got it right. And then I also show you here what ChatGPT 3.5 and 4.0 did, which I already talked about earlier, that 3.5 also did not get this question, and 4.0 got this question. Okay. And the reason why this lock problem was hard was because there were conceptual comments describing what happens, but there was no experiment to go and see what happens really. And so this shows you why experiments are useful in explaining concepts. Timing. So, like I said, I was chairing this session, but I was looking at my Google Docs and seeing how many people have opened the doc. I was really nervous, I'm telling you, because this is a challenging exercise for somebody who doesn't know much of threads, even those who have done threads. So 28 of the 40 students opened docs during class period. Okay? 11 of the 28 submitted code within 50 minutes, okay, to grade score. 23 or 28 submitted code within 90 minutes. And 9 out of 28 students submitted quiz answers within 90 minutes. And more would have submitted had I not gone and told them to resubmit later, and I'll tell you why I did that. I also had, this was not just a quiz, there was a survey also. So I asked them, okay, you know, how important were the new concepts you learned? Not what you already knew from concurrency, but what new things you learned. How important were they? And I gave them 4 choices. They could write anything, but I told them, here are 4 possible answers, not important. And one person, I think, or 2 said that. They must have been frustrated with what we taught. 32% said moderately important, very important, 38%. And I also had something, no student should graduate without knowing concurrency, and 24% went for that. So moderately important, you know, one person's reason was that, look, I knew this stuff before. I found it helpful to see how it's implemented code, but you know, it's not that important. So this is a good answer for somebody who's seen concurrency before. And here's a thing that should interest EDU-HIPC people. One person said, look, I'm a senior. I've gone through life without any concurrency. So concurrency can't be important. So it's a chicken and egg problem, right? You don't teach them concurrency, they don't realize it's important. And then he said, well, maybe the industry would like it. One person said, it's very important. I went to an interview, they asked me about concurrency. I didn't know it. And this was my favorite one. And I'm happy at least one person felt so. Now, there was a little problem answering this question because it's not clear from this first answer whether they think concurrency is not important or what new things they learned is not important. So I went and looked at the quiz answers and told them, please resubmit and make it very clear that it's the new concepts you learned, not what, this is not a judgment on concurrency. So that's why some of the quiz answers came in later. Okay, I also then asked them, you know, all my other classes were lectures. This was hands-on. So I said, look, you know, I couldn't help it. I couldn't be there, so I had to give you this hands-on thing. What if I had been there? Would you have preferred a lecture or hands-on? And 24% said lecture. Okay, 22, and I gave them an answer, not sure, little difference, and 38% people said exercise. And I went through each one of those answers and tried to figure out what they were trying to, why they liked one or the other. And they said lecture gives better explanations, serves better as an introduction, is more visual, promotes more thinking. I ask questions through Zoom chat, and so allows learning from peer responses, answers important conceptual questions more, does not require, so some of these guys had to take time after class to finish the exercise. They said, let's just finish then. And works for those who code at a slower pace. Okay? And the other alternative was, look, it's a more active form of learning, provides more depth, is tougher, is more self-paced, does not require the fast student to wait for the average student to provide Zoom answers. I do that. I wait for everybody to sort of say, okay, I've got answers, then they go and put their chat response. And does not require quick public Zoom responses, but people who are slow didn't like that, and gives reproducible examples. Okay? I would have personally given this answer. This was my perfect answer. It says, look, it was guided like a lecture, so this does as effective. That's what I thought it was. And one of the not sure reasons was, look, I want a hybrid model with the visual lecture introduction. And that makes sense. I showed you guys different colored locks here to show that each instance had its own lock. I couldn't show that in my Eclipse programming environment. So if you had time, maybe you could add this on. Okay, I'm at the end. So like I said, I was in cloud 9 when I saw my grade scope results at that workshop. Okay, I was just so worried it would be a total disaster. In terms of hardness, I didn't think it would be easy. So lectureless is viable, and if we can use GPT 4.0 perhaps, then even TA help may not be needed, and I have high hopes for that happening. And then you can add some pre-recorded video if the students have time to look at that, and you know these three bugs, you can try to go and introduce them with other concurrency mechanisms too. Okay, and it'll be interesting to see how to do that, and try it on beginning students. And you know, I'm looking, since I'm now sold on this idea, I'm looking for collaborations. I've talked to many of you individually, but those of you who've done the problem in that training workshop, please, I'm more than happy to work with you to adapt this problem to your environment. Okay, and that's